Hello, hello, hello! It's time to talk about photochemical smog, one of the most common forms of air pollution. We'll talk about what it is, how it's formed, what its impacts are, and what we can do to address it as a problem. So there are two types of smog. The sort of old-timey type of smog, which is what they call industrial smog or gray air smog. This is the historical fog that killed people in London in 1952, and it's just a result of sulfur dioxides and particulates that end up in the air from burning coal. Photochemical smog is a little bit different. They call it brown air smog. This is the modern smog that you see over LA or Mexico City or Beijing, whatever, and it's formed through a long chemical reaction, but the essentials is that nitrogen oxides, NOx, and VOCs, volatile organic compounds, combine in the presence of sunlight to form photochemical smog. We're going to go through that a few times, so don't freak out if you don't understand it the first time. So a little bit of background on industrial smog. This one you don't need to know as much about, but it's still pretty interesting and important. Results from burning coal, like I said, sulfur dioxide and some sulfuric acid forms, but also particulate matter. This will kill you really, really quickly. In some cases, the SO2 can result from not just burning coal, but also diesel, although not regular gasoline. Regular gasoline will not produce sulfur dioxide. It's formed under cool, humid conditions, which is what allowed it to form in London in 1952. They're doing building up their industry there. They're burning a lot of coal, and cars are starting to become more and more popular. The climate there is cool and humid, so it formed a giant mass of industrial smog that killed thousands of people in London. Here are some photos. You can see this is London Bridge, very smoggy. And here's some tenement houses in Britain. You can see that's the source of the industrial smog. Here's a nice infographic that shows you that the combustion of coal, but also fossil fuel combustion with diesel in your car, leads to the production of soot and sulfur dioxide, which forms sulfuric acid. And that's what industrial smog is, basically. Soot, sulfur dioxide, and sulfuric acid. The type of smog that we're going to spend most of our time talking about, though, is photochemical smog. And it's called photochemical because it's formed through a chemical reaction powered by the sun. Photo means sun. Think photosynthesis or photograph. Or I guess it means light, actually, like photon. And photochemical smog is a mix of primary and secondary pollutants. Remember, primary pollutants are ones that are released directly into the atmosphere, and secondary pollutants are ones that are formed chemically within the atmosphere. And that process, a mixture of primary and secondary pollutants that form, again, under the influence of sunlight. That's why it says photochemical. This will kill you very slowly, whereas industrial smog will kill you pretty quickly. This is a nice little graphic that summarizes pretty much everything you need to know. You've got primary pollutants like nitrous oxides and VOCs that make up some components of smog, but then some of these will react, like NO2 and VOCs. They will react in the presence of sunlight to form secondary pollutants like ozone. Okay, so how is smog formed? I like this infographic because this is photochemical smog. I like this infographic because it summarizes it up visually and very briefly, right? Nitrogen oxides, NOx, things that are released from your car, react with volatile organic compounds in the presence of sunlight. This produces ozone, O3. Ozone is a major component of smog, as well as particulate matter, like soot, dust, and ash. Now, it's important that you remember, and these two things will compile most of what smog is, but it's important to remember that there are some primary pollutants in here too. Nitrogen oxides and volatile organic compounds also make up the actual smog, as well as these other types of molecules called PANs, peroxyacetyl nitrates, and aldehydes. But you don't have to worry about those so much, but if you see those terms, they're chemicals that are found in smog, and they are secondary pollutants. So let's get into the details a little bit about how that works. And rather than a visual approach, let's take a sort of written approach. So nitrous oxides and volatile organic compounds react under the presence of sunlight, but they can also react under the presence of heat, which is why they are often reacting in coal-burning fossil fuel plants, but also your car engines, boilers, power plants. And the car engines is a big one, especially because car engines produce nitrous oxides, but they also can produce the heat that will then facilitate the formation of ozone. Because when nitrous oxides and VOCs react under high heat or sunlight, it produces ozone and other photochemical oxidants. Examples of these are the aldehydes and the PANs that I mentioned earlier. Photochemical oxidants are chemicals that are formed in the presence of light that oxidize other molecules. And what it means to oxidize something is it basically means to remove the electrons from other substances. That's why, and that's not good. You don't want that to happen. That will destroy molecules. And that's why they say, oh, eat your blueberries. It's got lots of antioxidants in it. Those are supposed to be healthier for you. Here's an image of the functional group of an aldehyde. If you've taken biology or chemistry, you may be familiar with this. It's just a C double bonded to an O and an H, in case you were curious. So you might be forgetting what a VOC is. I've mentioned it here a few times, but if you forgot, that's okay. I'm going to review it right quick right now. So a volatile organic compound. Basically, volatile means it evaporates very rapidly. And organic means it's got carbon in it, and a compound means it's just a combination of different atoms, molecules, right? They evaporate very quickly. They can be natural. Trees produce terpene, which is responsible for the formation of sap and resin, but also that piney smell that you smell of your pine trees or your spruce trees. But it can also be an anthropogenic source. And there are a variety of household chemicals and products that produce VOCs. Pretty much anything you smell is going to be a volatile organic compound. It's just a type of molecule, broadly speaking. And they range from harmless to totally toxic, like formaldehyde. Examples include paints, turpentine. Turpentine comes from the word terpene. Paint thinner, gasoline, methane is a VOC, ethanol, nail polish remover. All those things will evaporate very quickly, and they have a very strong smell. So in case you forgot what VOCs are, there you go. So let's review how smog is formed. I went through this diagram here. I went through it in words, and now I'm going to go through it with this visual blown up, right? So you've got nitrous oxides that are going to react with volatile organic compounds under the presence of sunlight to form secondary pollutants like ozone, but they also form things like aldehydes and PANs. These secondary pollutants and primary pollutants will combine overall to form smog, photochemical smog. Oh, hi Dora. Oh, you have a question? Great question. What factors affect smog formation? Well, let's find out. Good question, Dora. She's a very, very inquisitive young mind. Love to see that. So we need to go back to this diagram to think about the factors that are going to affect the formation of smog. The reactants or the ingredients of smog are nitrogen oxides and volatile organic compounds. Where do these things come from? Well, we just said volatile organic compounds come from a variety of sources, mostly synthetic chemicals that humans use. Nitrogen oxides, on the other hand, are produced by fossil fuel combustion, most notably your automobiles, the cars, the buses, trains, etc. So time of day is going to make a huge impact on that for a couple of reasons. One, the morning commute, right? Traffic jams with lots of people who are idling their cars, stuck in traffic, burning gasoline is going to produce a lot of nitrous oxide. More nitrous oxide produced early in the day during that morning rush hour is going to have a sort of a domino effect on the formation of smog. But smog also requires sunlight to form. So as the sun starts to rise and get more, the solar intensity increases, smog formation is going to increase as well. So as NOx starts to build up over the course of the morning and the sunlight gets brighter, smog formation starts to peak in the mid-afternoon because of that. And we'll go over that in class with some graphs. Wind also has a big impact on smog. Smog doesn't stay put. It's airborne particulates, right? This line down the middle, I believe this is taken in China, 4 days apart. So one day it's really smoggy. A few days later, the wind has relocated that smog elsewhere, and it's clear and blue skies. Unsettling fact alert, by 2050, 400 million residents of China will drive cars, meaning that the smog that those cars are going to produce is going to cover the entire western Pacific Ocean and ozone, which will eventually reach the United States. It's a little bit scary, a little bit unsettling, but as I'll talk about in a sec, there's a lot we can do to reduce smog formation. A third factor that can affect smog is topography. if you've got a city that has mountains all around it, or if it's in a valley or a basin, smog is going to get trapped in there a lot easier, right? LA is surrounded by mountains. Beijing is in a basin. Those are two great examples. Also, if it's by the water, which most cities are, the ocean, and to be specific, a cool breeze is going to help trap that air between the mountains and the ocean. So most of that pollution is going to get stuck over the city. And the fourth one, and this one is probably, along with time of day, the fourth one, thermal inversions can have one of the biggest impacts. So a thermal inversion, thermal means temperature or heat, and inversion means to flip, the opposite, right? So basically what happens is the temperature gradient that we normally see in the troposphere is flipped. Normally, when you go up in the troposphere, it gets colder as you go up, remember? But in a thermal inversion, that's flipped. The cold air is at the bottom of the troposphere towards the Earth's surface, and as you go up, it actually starts to get warmer. And what that does is it prevents the mixture of air, right? Warm air rises, but if it's inverted, the warm air is risen, cool air won't rise. It will stay trapped beneath that layer of hot air, and that's going to trap all sorts of air pollutants in that thermal inversion, most notably smog. Here's pictures from your book, right? Under normal conditions, it gets colder as you go up, so hot air rises. It allows for admixture between all the different layers of the troposphere. But during a temperature inversion, this axis here, I just pointed at my screen, but you can't see me in real life. It's normally warm towards the Earth's surface and cool as you go up. This gets flipped. It's a thermal inversion. So now it's cool towards the ground and it gets warmer towards the air, as you go up in altitude, I should say. And that prevents the mixture of air because the pollution and the air gets trapped underneath that layer of warm air, because cool air won't rise. It will stay sunk and warm air will stay risen. Dora, we can't understand you with your face mask on. I'm glad to see you trying to protect yourself, but you need to take it off. Okay, thank you. Oh, great question, Dora. Excellent question. Wow, really thinking critically. I like to see that. What situations can lead to thermal inversions? Because if you look at something like this, it's like, okay, how the heck does this even happen? And there are a couple of, Dora, move along. There are a couple of different situations. Here's a picture from Kazakhstan of a thermal inversion. You can see that line, very clear delineation between the cool and the warm air. That can be caused by warm fronts that are moving in or high pressure. It happens a lot in valleys and basins. So thermal inversions tend to happen when the radiation from the Earth is greater than the solar radiation received from the sun. And that tends to happen in wintertime and at night, where cities, when the sun's not shining as much, like in the winter or at nighttime, cities will release the heat that they have been sort of building up over the course of the day from absorbing the sun's heat, and will release that heat. That heat will start to rise, and the city itself at ground level will rapidly cool off at night once that heat rises. And the heat will rise and will stay trapped up there. Meanwhile, the city's cooling off, leaving a layer of cool air beneath. I'll show a demo in class that will demonstrate how that happens. It's pretty neat. Here are some pictures. This is a thermal inversion from the perspective of if you're standing on the ground. It kind of looks like a layer of air, right? Sort of in the middle of the troposphere, which is exactly what it is. Here's a thermal inversion from above. Very, very picturesque. This is a valley here. So there's hot air up here, and this air is cool. Cool air stays sunk, and hot air stays risen. The big issue with thermal inversions is they can trap smog and other air pollutants. And if it's happening over a city, right, like here, that all those air pollutants are going to stay in the city where all the people are, which only is going to increase the concentration of smog and air pollutants. It's going to increase their negative effects on your health and, of course, on the environment as well. And some of those impacts on the human health, right? It can burn your eyes, it can irritate your throat, it can also lead to depression, it can increase chances of heart issues like cardiovascular disease. It can, in some cases, it's been shown to lead to decreased immunity, so you're more likely to get things like pneumonia or a cold. It's been linked to skin cancer, damage to your central nervous system, inflammation in your lungs, headache, shortness of breath, wheezing, coughing. I was in New York City the other day, and I had trouble breathing. I could feel it. I'm a very sensitive guy, but I could feel the impacts of the smog on me just from spending like 12 hours in the city. So, oh look, it's Dora, and she looks awfully happy. Hopefully, this is an optimistic question. Dora, hit us with it. How can we reduce? Oh, Dora. See, this is why I like Dora, because she always wants to make a difference. She wants to fix the problems of the world. Thank you, Dora. What are you swimming in? Is that like some sort of pollutant? You should get out. It's probably contaminated. I would get out. But great question. How can we reduce photochemical smog? Again, we need to go back to our visual aid here. Smog comes from ozone. Ozone comes from nitrogen oxides, sunlight, and VOCs. We're not going to alter the amount of sunlight, but we can alter the amount of VOCs and the nitrogen oxides, right? And there are pretty simple ways to do that, right? If you drive less, you're going to you're not going to be using your cars as much. You're going to be producing less nitrogen oxides. If you take care of your cars, if you get them regularly checked up, if you make sure that you're putting a high quality gasoline in, if you are maintaining a high mileage per gallon, then you're going to, again, burn less fuel and produce less nitrogen oxides. You also can avoid products that release high levels of volatile organic compounds. That probably doesn't really apply to you guys so much, but if you're like a small business owner or you're working in an industry, you can try and reduce your consumption of things like paint thinners or turpentine or whatever. Avoiding using lawn equipment that is gas powered is a very specific example, but you can be like this guy who's clearly very inventive, attaching his lawnmower to a bike. But you could also use electric powered lawnmowers or leaf blowers, or you could do them manually, like with one of those old school ones, kind of like this. And the last one, the big one that you can do is don't idle your cars and avoid traffic. And the reason for that is because if you remember, ozone forms in the presence of sunlight when volatile organic compounds and nitrogen oxides react. Well, where do these come from? They come from your car. But in order for them to form from the combustion that's happening in your car's engine, that reaction to that forms nitrogen oxides needs heat. So only hot engines are producing nitrogen oxides, right? Cold engines don't do that. And by idling your cars, you're keeping your engines hot, thus contributing to the formation of increased nitrogen oxides. And then also, we have the Clean Air Act to thank in terms of addressing photochemical smog. This is the legislative side of things. You can look on the x-axis, we've got time, and on the y-axis, the bars represent the number of days exceeding the federal standard for ozone, and the red line just represents the ozone concentration in the air. And you can see that since I guess that's probably 1975, it's dropped significantly, and we're actually almost at the point where we're below the federal health standard. Right? This is overall for the entire U.S. Some places like L.A. and major cities, New York, are way worse. We don't really have smog around here in Greenwich. But as a whole, the general trend is down, which is great. And this is just ozone, but that's true for all of these major pollutants that we've been talking about in class. Carbon monoxide, nitrous oxides, and VOCs, not down a lot compared to some of these other ones, like lead's down 99%. But these are still, it's pretty significant, cut in half at least since 1970, if not more. So we have that to be thankful for, the Clean Air Act, supporting it, supporting the regulations and restrictions that it applies to automobiles is really, really important. So if you see that in the news, read up on it and see if you can draw connections to what we've been talking about in class. Okay, so that's it. If you've got questions about it, don't worry. We're going to talk about it in class. Write your questions down, bring them to class, and I will see you next time. Bye.